Okay, everybody, welcome to Philosophy of Physics at Oxford. My name is Simon Saunders, and it's with great pleasure that I introduce Eddy Chen in the Philosophy Department of UC San Diego, who will talk on the Wentaculus, density matrix realism meets the arrow of time. Well, if the Wentaculus reminds you of something, it's because Eddy did his graduate work with David Albert, Barry Loewer, and Shelley Goldstein at Rutgers. But it is Wentaculus and not the Mentaculus, so some independence there. I'm also pleased to relate that Eddy was first drawn into philosophy of physics during his visit to Oxford as an undergraduate, where he was bamboozled, tutored by Chris Timpson. Chris, I think, is in the audience, so a nice connection there. Eddy doesn't only work in quantum mechanics and statistical mechanics. His recent ideas on vagueness, both in ontology and physical laws, has been making waves. He was on the front cover of New Scientist last year. But today, it's the Wentaculus, the density matrix realism meeting the arrow of time. Eddy, the floor is yours.
Thank you so much. I want to thank Simon for the kind invitation. It's an honor to be with you all today. I prefer to meet with you in person. Like Simon mentioned, that my interest in philosophy of physics started in Oxford, studying philosophy of physics with Chris Timpson for I think the Hillary quarter of 2012. So it's almost 8 years ago. I was studying seminars with Simon and Harvey and David in philosophy of physics. So even though the stay was brief, it had a huge impact on me. And it kind of gave me motivation to study philosophy of physics when I was at Rutgers. So it's great to be back virtually and to present my latest work to you all. Okay, so here we start. So the Ventaculus, density matrix realism is the arrow of time. Some background ideas. So here are two of the most difficult problems in the foundations of physics. The first one is what gives rise to the arrow of time if the laws of nature are symmetric between past and future. And two is what is the ontology of quantum mechanics? Now, there are some answers to this question in the literature in terms of, say, the past hypothesis for the first question, and quantum state realism for the second question. But these answers have the drawbacks. They're unsatisfactory for some reasons, as I'll explain. Now, the conventional wisdom is that the quantum puzzle and the puzzle about the arrow of time are independent puzzles. But are they really independent? I suggest that a new way to think about the second one gives us a better way to think about the first one. So here's the proposal. The key is to be open to or to endorse, to accept following thesis called density matrix realism. So as I understand it, it is the thesis that the quantum state of the universe is objective. It is not subjective. It is not expressing ignorance. It is objective. And moreover, it is impure. So this is in contrast to wave function realism or realism about the pure state. So here I think that we can allow a wider reading of density matrix realism that allows both pure states and impure states. But I think for simplicity and to avoid causing confusion, I'm just going to stipulate that by density matrix realism, I mean this mixed state realism of the quantum state of the universe. Okay, I'll expand on this idea later, but here's the kind of key idea. So the goal of this talk is to discuss a new way of thinking about time's arrow in the quantum universe that presents a more unified solution to both puzzles. It is more satisfactory than general answers and the past hypothesis or pure state realism. And it has interesting implications and open questions for both physics and philosophy. I call the theory the Wentaculus. So it is intentionally kind of a pun on the Mentaculus of Albert and Loewer. For them, this term derived from a famous movie called The Serious Man by Coen brothers. For Wentaculus, the key difference is that the fundamental quantum state is given by W, a density matrix. That's why it's called a Ventaculus. Okay, I call this W not rho because sometimes rho is used for other density functions, probability functions, and so on. And this has this subjective probabilistic field, but W for me is a fundamental density matrix. And I'll explain that in a second. So metaphorically, what we do is trying to kill two birds with one stone. So here the stone is the Ventaculars, and the two birds is one, the problem of the quantum state. And the problem of the past hypothesis. Okay. It still does have a quantum state of the universe, and it still has some kind of boundary condition of the universe. But I think what Wentaculus suggests is something more reasonable and satisfactory. Okay. Now, a tree is known by its fruits. So the Wentaculus shows the density matrix realism, which might be, you might think, empirically equivalent to the wave function realism picture, right? But I think the Ventaculus shows that density matrix realism is theoretically fruitful and might be superior to the wave function realism counterpart. So because it kind of solved these two puzzles, and for me, biographically, I came to this idea because I was thinking about and worried about the nature of the wave function in Bohm theory, in average theory, in GW theory. It seems to me that the existing solutions are not fully satisfactory. You have the high-dimensional field picture, multi-field picture, the law picture. All of them have drawbacks. So if I were to give a different talk, the title of this talk, it will be called The Ventaculus, or How I Learned to Stop Worrying and Love the Quantum State. And I can't resist showing this picture of the Ventaculus. Okay. All right. So here's an overview of this talk. I'll first talk about density matrix realism, and second, the arrow of time, and the third, which is the focus of this talk, is on the Ventaculus. Okay, to begin, density matrix realism. So as I mentioned, it is a thesis that the quantum state of the universe is subjective, it is impure. So let me unpack this definition. So there's a unique one. So there's a unique quantum state. The universe is kind of basic, fundamental, that's prior to other kind of derived quantum states. So it's in contrast to the idea of, say, you have a universe, but two different quantum states, say a psi and a rho. I think this is suggested in some of the writings of David Wallace, 2012 and 2013. We suggest that we can reinterpret rho not as a probability distribution, but as another realist quantum state. So on my picture, there's only one quantum state, basic quantum state universe, this density matrix. Okay, so the quantum state universe is in contrast to quantum state of the subsystems, quantum state of this particular experiment, this particular setup, and so on. So because of entanglement, the universal quantum state is the basic one, designated by W. Now W is objective. So it is not subjective. It is not based on our ignorances, preferences, but it is something that's real. The different ways to understand how real it is, there is the understanding of, say, high-dimensional field picture. Right? There's multi-field picture. They're both compatible with this. There's nomological picture, understanding W as something like the law of nature. Okay, that's the one that ultimately I prefer, and I think made plausible by density matrix realism. And it is impure, so it is not pure. Okay, so we have an objective and impure quantum state universe given by W.
Eddy, can I just ask, when you say it's the unique quantum state, are you saying that the quantum state is not contingent, so there couldn't be different universes with different initial conditions?
That's a good question. So for density metric realism, it is contingent. But for any actual universe, the actual quantum state of the universe is unique. Right, but there are different possible quantum states. But on my picture, given what I postulate later, is going to be the result of density metric realism in conjunction with my postulate that there is a unique possible density matrix of universe. Yes.
Actually, Eddy, can I just jump in too? Is it degenerate, this density matrix of the universe?
Degenerate?
Yeah, is it degenerate? Is it, if you diagonalize it, does it have equal values in the diagonal?
So it's going to depend on the particular universes. So for me, yes, but for in general, the different parts, so you can have all kinds of mixed states in some subspace. Doesn't have to be degenerate, right? So it can be completely generic.
Right.
If it's impure, though, it will be degenerate in its diagonal basis.
Well, it doesn't have to be. But anyway, let's let the speaker get on. Yep.
Sounds good. Okay. So this idea of density matrix realism is related to other proposals in literature. One of the most clear examples, I think, is in this paper by a dear friend of mine, the late Douglas Duo, who sadly passed away recently due to COVID, and co-authored with Charlie Goldstein, with Tomoko, Nilo Zangi, published Foundation Physics, and also related to other paper by Owen Maroney in the same year in the same journal. And these two papers actually all trace back to the fundamental equation of these two papers, which is called W guidance equation for Bohm mechanics. Goes back to John S. Bell paper on the de Broglie-Bohm delay choice and so on. And this is where John S. Bell contrasted a density matrix guidance equation in pilot wave to a pure state guidance equation pilot wave. Okay. And also it is related to David Wallace's work on the average interpretation. In his book, 2012, there are sections on mixed states of universe, considering reasons for and against it. There's another paper by Valialori and co-authors on primitive ontology, where they go through several different ways to make the wave function quantum mechanics into a density matrix mixed state quantum mechanics. So they consider ways to adopt GRW and Bohm and even averaging quantum mechanics using fundamental W. Okay. And this recent paper coming out in BJPS by Katie Robertson on the Gibbsian understanding of system mechanics. And she considers how density matrix realism can help the Gibbsian understanding of entropy and derived second law. Okay. Now to review, so density matrix realism is in contrast to wave function realism. Now for wave function realism, we have the following theories. I call them psi-Bohm mechanics, psi-aberrating mechanics, and psi-GRW collapse theory. All of them have in common is a fundamental objective wave function that appears in the dynamical equations. In Bohm's theory, what guides particles is the universal wave function. In GRW theory, what undergoes collapses is the wave function of the universe. Some function of the probabilistic function, right? So probability is given by function of the previous wave function. In the aberrating picture, the universal wave function is the basic fundamental level of reality that give rise to emergent say branches and observations. Okay. Oh, here's a review of this topic in field compass. Okay, so for density matrix realism, I call them W Bohm mechanics, W aberrating mechanics, and WGRW collapse theory. So what they have in common is going to be the same thing. That is density matrix W now enters into the dynamical equations. So on Bohm's picture, instead of having a wave function guiding particles, it's going to be dq dt is going to be given by the gradient of the density matrix, mixed state. Right, usual constants and so on, right? In the GLW picture, what undergoes collapses is no longer the wave function, but from the density matrix. So T plus is given by some kind of collapse mechanism of the previous density matrix. On the written picture, it's no longer the wave from the branches, but a density matrix that branches. So this might introduce more branching structure into the ever-rating multiverse, given that macro states in systems mechanics can branch as well as the wave function can branches. So we have three versions of density matrix realism: the Bohmian version, the ever-rating version, and the GLW version. I'm going to show you the equations later. Okay. So conceptually, we may ask, are they really different? Moreover, are they different in terms of empirical predictions, what we can observe? So the question is whether wave function realism, in some sense, is empirically equivalent to density matrix realism. More precisely, for example, take the Bohmian version. Is psi BM empirically equivalent to WBM? Is there any experiment you can do to perform such as to reveal difference between the two or confirm one over the other? If yes, if they are empirically equivalent, then we'll have the same confirmation for both theories. If no, and there will be different predictions for experiments, so we can detect which one is correct. So I think the answer is yes, but the question is delicate. So there's a quick kind of one-line argument why they're equivalent. Take Bohmian mechanics, for example, and that's kind of clear cut. You have the probability distribution of particle histories, or and in time t is given by, say, x is in some, it's going to be given by, so on a wave function picture, it's going to be given by psi. But given a random psi, chosen at random from a collection of wave functions, the random is given by density matrix W. Say this is random is given by W. Then probability distribution is going to be given by W. Sorry. And this is going to be the same thing as we have in the W Bohmian mechanics. We have, so the probability over trajectory of particles are going the same, and that seems to show that they're empirically equivalent. But what hasn't been shown is whether the macroscopic histories are exactly the same. So I leave that question set aside for now. Okay. Now, on both theories, wave function realism and density matrix realism, this question is, what does the quantum state represent? So for psi and W, what are they referring to in the physical world? And it's difficult to think about it being some kind of field, because there'll be a high-dimensional field on high-dimensional configuration space, a low-dimensional field and multi-field, but it's kind of odd features. The nomological view, which I think is promising, still faces the problem of complexity. Given the generic wave function universe, or density matrix universe, it is going to have so much information within them. And it is going to be so gerrymandered on configuration space. It is difficult to imagine there'll be a simple closed form mathematical expression expressing them. So you think of psi as a law, and laws have to be simple. But psi is complicated. So that's not a good way to go. And similarly for W, right? If W is complicated, then it's not going to look like a law of nature. Okay. That's just a brief overview of the quantum mechanics issue. Let's now get into the error of time. So what explains the error of time? So briefly, we have macroscopic irreversibility, say ice melting and gas dispersion, and they don't happen in the reverse order. But we have microscopic reversibility, say in the Everettian picture, in the Bohmian picture, or in classical mechanics and so on. The fundamental equations of motion are future and past reversible. They don't prefer a direction. They allow gas to melt. They allow they allow ice cubes to melt. They allow ice cubes to form spontaneously. So what explains this apparent irreversibility in our experiences? One promising explanation is a cosmological one, now called the past hypothesis. Roughly says the universe is in a low entropy state, or at one boundary of space-time, there is a low entropy macro state. Right. So given the low entropy macro state, now we have the development of higher and higher entropy. So in the Boltzmannian picture, we have the following idea that suppose we have a phase space of the universe, and we have the biggest macro state being thermal equilibrium, and the initial micro state x0 studied in some macro state m0 with very small volume, which corresponds to very small low entropy in Boltzmann sense. And this is a very small region. Now, this is not faithful because if you do draw it faithfully, you cannot even see this dot, right? You cannot even see this region in phase space, so small. However, Boltzmann's conception, given this, take a kind of randomish walk in phase space, right? Most likely is going to end up in the equilibrium macro state, where most likely it's going to go through bigger and bigger macro states, and there's going to be increased entropy trajectories. Okay. So the question of the past hypothesis, which is select this particular one, is that it doesn't seem to be derivable from other laws of nature. Both pH, the past hypothesis, and the negation of pH are compatible with the fundamental equations of motion. So you can start from a high entropy region, you can start from a low entropy region. It doesn't seem like we can derive this past hypothesis from laws of nature, other laws of nature. So it seems like if you have this explanation, it has to be axiomatic. It has to be one of the axioms in the theory to derive this macroscopic regularity of times arrow. And moreover, given the role it plays in explaining the times arrow, and given the times arrow seem to be nomological regularities, playing the role of laws of nature, then the past hypothesis seems to be nomic. It seems to be a law of nature. Now, given it's axiomatic and nomic, they seem to favor the view that it is a fundamental law of nature, on a par with the equations of motion. And the obvious issues here, one of them is that the past hypothesis is boundary condition, it's not a dynamical law. So how can it be a law of nature, fundamental law of nature? And the second, I think, is more subtle, is that it seems to be a vague postulate. And any way to remove the vagueness, or any kind of precise way to pick up the boundary of past hypothesis region, is going to lead to some arbitrariness. I call this untraceable arbitrariness. So let me explain this briefly. So suppose I choose an exact boundary on phase space. Instead of the fuzzy ones we had before, we have an exact one that privileges a particular gamma zero. So gamma zero is the precisification of M0, and gamma zero prime is not. So gamma zero is the correct precisification of M0. The problem is, unlike constants of nature, unlike other laws of nature, gamma zero, the boundary of this, is untraceable. It does not leave any trace in the material ontology of the world. So if I change the boundary of gamma zero slightly, right, slight change of boundaries like this, in most worlds compatible with the original one, doesn't feel any difference. However, if you change, say, the gravitational constant G, right, if you change G, from 6 point something to 6.5 for something, right? That's going to, even though it's a small change, there's going to be a manifest difference in almost every world compatible with the original one. Almost every world compatible with the original value is no longer compatible with the new law. There's not going to be, so G, the value of G is traceable, but the boundary of gamma 0 is not. So I think the best way to understand the past hypothesis is in terms of a vague law. And that does require us to revise our understanding of conception of laws of nature, that they can be vague. But I will show that this problem is not a problem for the Wentaculus. Okay. Now for standard quantum versions of the past hypothesis, when you have a wave function, right? So you have a wave function version of the past hypothesis. It says initial wave function belongs to some particular macro state, where this is given by some collection of subspaces in Hilbert space. Faces the same kind of problems as the classical version of the past hypothesis. We had the same idea about the question about the past hypothesis status, and is a boundary condition law, so not a dynamical law, and has the same problem with vagueness and arbitrariness. The new problem, however, is a dualism of two kind of probabilities, right? So we have now the quantum probabilities of, say, the Born rule, but also we have the mechanical probabilities, because the past hypothesis by itself is not sufficient. Also, we need a uniform distribution over the macro state M0 that gives you a typicality measure or a probability measure. It says almost all or most points will evolve to high entropy states. But without this measure, this is not enough. So the two measures of probability, system mechanics and quantum mechanics, they seem to be disjoint. They seem to be distinct. And I think all things being equal, it would be preferable to have a theory that unifies the two, that give you an explanation of why these two are connected or how they come out of the same thing. Okay. Now let me get to the Ventaculars, section 3. Okay. So as we've seen, having the wave function picture and having the past hypothesis solve some puzzles, but they leave other puzzles unsolved, introduce different difficult problems of laws of nature and vagueness and initial quantum state. But I think the Ventaculus whole the problem is to solve them in a satisfactory way. So what is a Ventaculus? Well, it is a collection of density matrix realist theories, and it's inspired by the Mentaculus of Albert and Loewer. So recall the Mentaculus, right, has the following postulates. So the classical Mentaculus is in classical mechanics. We have fundamental dynamical laws of motion, we have F equals ma, and the past hypothesis that says the initial microstate of the universe is in some particular macro state M0. Now we can, given the choice of arbitrary parameters, we select a particular precise boundary, gamma pH. And given the macro state M0, we postulate a uniform distribution over the microstates compatible with M0. And these three are supposed to give you a probability map of the whole world, because they assign a probability to every macro state, every region in phase space. Suppose you want to know the probability of Biden and Harris winning the re-election in 2024, as long as you can express that proposition in terms of some region of phase space, some macro state in phase space, that's going to get a determinant value probability. That might seem too much, right? So you might understand this statistical postulate less seriously, maybe as a typicality measure, not a probability measure, that give you kind of coarse grain values for only values at extremal points, almost 1, almost 0. Okay. Now, the classical Mentaculus can be given a quantum update. So for the quantum update, we can change F equals ma to the Schrodinger equation, and the past hypothesis into a wave function formulation that the initial wave function psi 0 of the universe lies inside a particular low-dimensional subspace, HPH. So here we assume that so the energy shell of the universe can be decomposed orthogonally into many different subspaces, H1, H2, H3. And one of them, say, is HPH, that corresponds to the macro state of low entropy and, say, high pressure or density of the early universe. And this one has low dimension that corresponds to low quantum Boltzmann entropy. So to say that the path hypothesis, the wave function universe lies within this low-dimensional subspace is to say that the universe started in some low-dimensional macro state. However, this is not enough because there are going to be anti-entropic wave functions. So we postulate a uniform total distribution over wave functions compatible with HPH. And that's going to be given by, say, take HPH and unit sphere in HPH. That's all the unit vectors in HPH. And that's going to be a sphere. Take the surface area measure of that sphere and normalize that. That's going to give you a normalized probability distribution over all vectors within HPH. So mu HPH. So given these three, we can say they support the plausible conjecture of quantum Boltzmannian quantum system mechanics. That is, typical initial wave functions, where typically the universe started in low entropy macro state and grew to higher entropy states. Okay. So the quantum Mentaculus can be given a density matrix update. This is a further update. So before we have classical mechanics and psi quantum mechanics. Now we have W quantum mechanics Mentaculus. So for this version, we can take the von Neumann equation to be the fundamental equation governing WT. So it generalizes the Schrodinger equation for psi t. And we can postulate, instead of the path hypothesis, something similar that says the density matrix is entirely within the subspace. So the trace of that together with IPH is projection onto this subspace, HPH. So trace of this and this is equal to 1. And moreover, there are many density matrices compatible with this path hypothesis. So you can use uniform measure of such density matrices. And this measure actually is easy to construct. You can take the space of all self-adjoint positives and trace 1 operators in this Hilbert space. And that's going to give you a space. And that space has a natural volume. And you kind of divide the volume by normalize this. And that's going to give you a probability distribution.
Eddy, I'm sorry, can I just interrupt a moment? Do you mean to still be on the quantum Mentaculus page? Because it hasn't changed for a while.
Oh, sorry. Yeah.
Oh.
Somehow it stopped working. Let me actually stop share for now. And sometimes, yeah, still sharing. Okay. Okay, now it's working again. Thank you. Right. So the density matrix version of quantum Mentaculus is as follows. We have a von Neumann equation, and we have a density matrix version of the path hypothesis, and we have uniform distribution over density matrices within the path hypothesis. Right. So, okay. That's the Mentaculus in 3 versions. Classical mechanics, psi-QM, and WQM. Now, so far, each psi-PH quantum mechanics and each WPH quantum mechanics admits many choices of initial quantum states. The initial subspace, HPH, is compatible with many wave functions. And the initial subspace is compatible with many density matrices. Can we do better? Can we somehow narrow down the initial choices to exactly 1? So, right, okay. I think we can. So I propose that we can use the past hypothesis to pin down a natural initial quantum state in the following way. The quantum state universe is given by a density matrix rather than a wave function. So density matrix realism. And the second proposal is called initial projection hypothesis. There's a natural density matrix in HPH, the normalized projection operator, this divided by the dimension of HPH. So the projection operator does nothing to vectors already inside the subspace. And it is the simplest density matrix you can think of on any subspace. And this one diagonally has all entry 1 given the normalization. So it's going to be something like this 1, 1, 1, 1, and 0 elsewhere. And this corresponds to the HPH subspace. And all of this corresponds to the energy shell. So you have a particular subspace of the energy shell being selected as a Lorentz macro state. And you have the simplest density matrix 1, 1, 1, 1 in that subspace. And that's the initial quantum state of the universe. Okay, so this gives you the Ventaculus. So here's the formulation. Only 2 laws. 1, the equation is given by the von Neumann equation for time evolution. So W evolves unitarily by the von Neumann equation given by Hamiltonian operator H bar. Now for the GRW theory, it's going to have random interruptions of this unitary evolution by collapses. But for Bohmian aberrating version, this is the evolution equation for the quantum state, W. And the second postulate is the initial projection hypothesis. At the temporal boundary of the universe, the density matrix is the normalized projection onto HPH. So this thing. And you realize that there's no accompanying statistical postulate. Because given this hypothesis, there's only one unique possible initial quantum state. That's why we don't need a property distribution over initial quantum states. Now, this Ventaculus started from the measurement problem. So we have to combine this with the solution to the measurement problem. So we have 3 versions again: the Bohmian Ventaculus, the aberrating Ventaculus, and the GRW Ventaculus. On the Bohmian version, we have, well, still initial projection hypothesis. Now the distribution of particle locations at T0 is given by this, right? And the von Neumann equation governs how the quantum state evolves. Now the guidance equation is the key difference. So instead of having, say, a gradient of psi, we have gradient of the density matrix. Okay. So the 4 equations are the fundamental equations of Bohmian mechanics, the Bohmian Ventaculus. The aberrating version is as follows. We have a projection hypothesis, pinned down particular initial density matrix W0, the von Neumann equation. Now this is all you need for the pure aberration interpretation, without any additional stuff, additional variables, additional modification. But if you're like me, prefer something in the physical space ontology, you have you can add this equation of mxt, the mass density function, given by the density matrix of the universe again. So this is the inner density operator that acts in the following way. So this gives you a kind of a function on physical space-time and derived from the density matrix of the universe. Okay. For the GRW theory, we have the following equations. So instead of having the spontaneous collapse given by this wave function equation, right, where the lambda is the collapse rate operator, we have collapse on the density matrix itself, Wt plus equal to this thing. And moreover, you can define further local variables in a similar way as mxt and flashes in the usual way. So that's the three versions of Ventaculus: the Bohmian Ventaculus, Everettian Ventaculus, and the GW Ventaculus. Now let's apply them to our problems, the two problems before, the quantum mechanics problem and error of time. Let's think about the nature of the universal density matrix and the status of the initial projection hypothesis. On the first one, we propose the following. So the initial density matrix now on the theory of Ventaculus is nomological, and subsequent WT is derived from W0 for all other times other than T0. Or the probability of WT is given by W0 on the GW theory. Okay. So this supports nomological interpretation of quantum state because W0 now generates motion. It is simple, it is fixed by the theory, and does not represent things in the ontology. So this is in parallel to the classical mechanics equations. Analogy with Hamiltonian function in classical mechanics. The Hamiltonian function is nomological because it generates motion, it is simple, it is fixed by the theory. The interpretation here is that H is not ontological, but nomological. It is not in the things category. It is in the category of laws of nature. H is encoding the laws of force interactions, for example. How things move depends on H. And H itself is simple. So similarly, I propose that W0 is such a simple law. So let me just write out the explicit equation for Bohm's theory. For the Bohmian Ventaculus, you have the guidance equation, dq over dt equal to this thing. Now, before I had WT here, I can re-express this in terms of WT0 with the time evolution operator, both of which are simple. And this will give you this equation. So you see that we have, in classical mechanics, dq over dt given by gradient of something, a derivative of something, derivative of h. So here we have the gradient of something, a function of w. That's the analogy with classical mechanics. And similarly for the Everettian picture and the GW picture, we have, for the Everettian picture, we have this equation, right? So once you have the W IPH T0, and you have time evolution operator, and we can have M x T0, M x T1, ... Okay. So the key claim here is that the initial quantum state of the universe is simple. Why is that? Well, if the past hypothesis is simple enough to be a law, then the projection onto the past hypothesis subspace is simple enough to be nomological. And here I'm assuming that the past hypothesis can be simply characterized in terms of, say, something like the wide curvature hypothesis, something like Ash-Tecker and Goop's generalization of wide curvature hypothesis in quantum machine. Now, if this turns out to be not simple enough, then we're in trouble. But the trouble primarily is on the past hypothesis, because if that's not simple enough, then we lose the promising explanation of time's arrow. Okay. What about psi? Well, this move, the nomological interpretation that becomes more natural, is not available for standard theory that take psi to be the objective quantum state. The simplicity of psi is not guaranteed by the simplicity of the past hypothesis. Given psi in some subspace, it takes much more information to pin down the exact psi 0 than pin down HPH. Think about just like a high-dimensional vector space. It takes more information to pin down a particular vector than, say, a plane. So the subspace contains less information than individual vectors in the subspace. So if this is simple, it does not follow that this is simple. Maybe some other route is possible, say given by the Wheeler-DeWitt equation suggests some idea of simplicity of the wave function, but I won't pursue it here. Now, given the past hypothesis is simple enough, W is simple enough. And this is simple, this is good news for quantum state realism, because if you take density matrix space realism and take initial projection hypothesis to be a law, then the quantum state WT0 is nomological. And this gives you reason to be optimistic that the quantum state can figure in the best system of the Humean metaphysics framework, or even a governing view that says the quantum states govern how things move. Okay. What about the initial projection hypothesis, IPH? Now, IPH is directly involved in dynamics, which we write it into the dynamical equations. It does not face the line between nomic vagueness and arbitrariness. Why is that? Well, WT0, so say in the Bohemian version, we have WT0 guiding the some function of this guiding the particle velocities. This is both the micro state and the macro state at T0. It does enter into the fundamental equation of motion, but also it pins down the subspace for the low-dimensional subspace. So its exact value makes a difference to how things move microscopically. So before we have the wave function picture, some function of the wave function. But changing the boundaries of the passive part of the subspace typically does not make a difference to the values of the wave function inside the subspace. So there's a key difference between W and psi equations. The W is both the macro state and the micro state at T0. And this is good news for fundamental exactness. That is, suppose we have IPH being a fundamental law of nature, then it's no longer the case that we have to choose between vagueness and arbitrariness. We can maintain exactness without committing to some problematic case of arbitrariness. Furthermore, the probability dualism is gone. We don't need a probability distribution over initial quantum states. There's only one possible choice. So the only fundamental probability distribution is the quantum mechanical one. And that is good for theoretical economy. We don't need to invoke both, say something like the Bohr rule and the set of mechanical postulate. So this is no longer needed. The quantum mechanical one is the only one we need. Okay, so since I'm at Oxford, virtually I have to mention the Everett interpretation more. Now, the Ventaculus is interesting news for Everettians. So for the Everettian version of Ventaculus, we have WT0 and unitarily evolved to W0. Now, if this is fixed by IPH, simple law, and this is fixed by the Van Neumann equation, then this is fixed at all times. So the entire trajectory, entire history of the quantum state of the universe, the multiverse, is fixed by the laws of nature. So this is strongly deterministic in the sense of, so Parallel 1999 says, not just a matter of in the future being dependent on the past, but the entire history of the universe being fixed at all time by some precise mathematical scheme. So there's a unique quantum history in the Everettian version. That's interesting, I think, to think about strong determinism and questions of, say, contingency and possibility. So how should we understand contingency? Now it's going to be completely emergent. There are no nomological possibilities beyond the actual one. So the actual world alpha represents the entire multiverse, is the only possible one. So this is the singleton set alpha is set of all possible nomological possibilities. I think this might actually be compatible with L. Wilson's new book on the nature of contingency, that Wilson trying to suggest that the everything picture is the foundation of contingency in some sense. And the Ventaculus is helpful in that regard. Okay. So far we'll talk about quantum mechanics non-relativistically. So if you only have a cosmological theory with your quantum gravity, perhaps not all assumptions will hold. But we can generalize this procedure given that we have a full Hilbert space. So if this is given to us, then maybe we can use simple principles, if there are any, to determine the initial subspace, H0 in H, right? And you can choose a natural quantum state in the subspace, the projection, normalized by the dimension. So this thing can still work as long as you have a Hilbert space and the simple principle to go to the simple subspace. And in the end, the natural choice will be simple and unique. So I think this can be generalized to other conditions. So one idea I'm looking at right now is the proposal of Ashtaker and Gupt, 2010, with generalized Penrose by curvature hypothesis to quantum regimes. I call it quantum by curvature hypothesis. And they do have a Hilbert space, and they do have quantum mechanical laws for loop quantum cosmology, although simplified. And in that case, we can start from the Hilbert space to the subspace and project. In their case, though, the dimension is infinite. So that's kind of a curious issue. I think of two ways to think about that. One is we do not normalize the initial subspace. So WT0 equals to just I0, and that's fine. Now the probability can emerge at the subsystem levels, where we have, say, system of this experiment. There might be a finite dimensional Hilbert space of this particular experiment E, and there you can still have a dimension of the subspace, and counting dimension give you some kind of notion of probability. But in the universal level, you can relax this assumption of normalization. Okay, so that's still work in progress. All right, so let me wrap up as my time is close to the end. So in conclusion, density matrix realism is theoretically a fruitful position. In this talk, we've shown its fruits by using the Ventaculus and baryon nature of the quantum state, and the past hypothesis, nominal vagueness, strong determinism, and probability monism. And there are many more issues to explore and more depth we can go to say these things more carefully and systematically. But I think it's interesting that if the Ventaculus is true, then the laws of nature determine not only time evolution, but also initial quantum state. And that possibility is actualized by the initial projection hypothesis. And then for me, I think it's quite exciting and seems to worth investigating further. Okay, so here's some papers on this topic, which are all on my website. All right, thank you, the end.
Okay, thank you, Eddy. A round of applause, really. I don't know if people can free up their audio. It was a fascinating talk.